S7-1200 PLC control of electric retractable doors. In our daily lives, electric retractable doors are widely used. Whether in residential areas, shopping malls, parking lots, or factory entrances, electric retractable doors are prevalent. They bring convenience to our lives while also enhancing safety and efficiency. But have you ever wondered how these doors are precisely controlled? What kind of brain operates behind the scenes? In this lesson, we will learn how to use the S7-1200 PLC to control electric retractable doors. First, let's understand the content of this task. The operation of the electric retractable door is managed through PLC programming. Pressing the up button raises the door, and pressing the down button while it is rising immediately stops the upward movement and starts lowering the door. Similarly, pressing the down button lowers the door, and pressing the up button while it is lowering immediately stops the downward movement and starts raising the door. When the door reaches the upper or lower limit switch, it stops moving. Let's analyze this task in detail. The door's upward and downward movements are primarily achieved by controlling the motor's forward and reverse rotation. Pressing the up button causes the motor to rotate forward and lock, ensuring the door continues to rise. Pressing the down button causes the motor to rotate in reverse and lock, ensuring the door continues to lower. If the door is rising and the down button is pressed, the door will lower. If the door is lowering and the up button is pressed, the door will immediately rise. Therefore, programming is required to switch between raising and lowering at any time. This task involves several key instructions, including set, reset, positive, negative, multi-set, multi-reset, and edge for scanning RLO signals. Here is a detailed explanation of the application of each knowledge point. 1. Set and reset. The set writes a 1 to the specified address, setting the specified address bit to 1 and holding it. This instruction executes only when the result of logic operation of the coil input is 1. If no signal flows through the coil, RLO is 0. The signal state of the specified operand remains unchanged. This instruction is generally applied to Q memory bits or M memory bits. The reset writes a 0 to the specified address, resetting the specified address bit to 0 and holding it. This instruction executes only when the result of logic operation of the coil input is 1. If a signal flows through the coil, RLO is 1, the specified operand is reset to 0. If no signal flows through the coil, RLO is 0, the signal state of the specified operand remains unchanged. This instruction is generally applied to Q memory bits or M memory bits. The ladder diagram and timing chart for the set and reset are shown above. In the ladder diagram, when I0.0 is connected, the set sets Q0.0 and holds it, i.e., Q0.0 equals 1 is connected, similar to a coil self-locking. Only when I0.1 is connected, the reset can reset Q0.0, i.e., Q0.0 equals 0 is disconnected. The timing chart shows the signal change process of Q0.0, indicating that when I0.0 is 1, Q0.0 is connected, and when I0.1 is 1, Q0.0 is disconnected. 2. Positive and negative. Edge signals include positive and negative. The positive is the transition from 10% to 90% of a high-level pulse signal, generally considered as the transition of a digital signal from 0 to 1. The negative is the transition from 90% to 10% of a high-level pulse signal, generally considered as the transition of a digital signal from 1 to 0. The diagrams above illustrate the positive and negative and their connection states. Diagram A shows the positive, and diagram B shows the negative. The question marks above typically represent the input memory I bit, and the question marks below typically use the intermediate memory M bit as an accompanying signal. When the upper address receives a positive, the lower address stores the information. These diagrams show examples of the application of positive and negative and their timing charts. It can be seen that when I0.1 receives a positive, the output coil M10.1 generates a pulse lasting 1 cycle at the positive of the I0.1 signal. When I0.2 receives a negative, the output coil M10.2 generates a pulse lasting 1 cycle at the negative of the I0.2 signal. By using positive and negative, the long-duration signals of I0.1 and I0.2 are converted into short-duration signals M10.1 and M10.2, making this a common method for shortening signals. In the latter diagram above, when I0.1 changes from off to on, i.e., I0.1 changes from 0 to 1 at the positive instant, the positive connects M10.1 for 1 scan cycle, then the set sets Q0.0. When I0.2 changes from on to off, i.e., I0.2 changes from 1 to 0 at the negative instant, the negative connects M10.2 for 1 scan cycle, then the reset resets Q0.0. In the program, M0.1 saves the value of I0.1 from the previous scan cycle to compare it with I0.1 in the current scan cycle to determine if a positive has occurred. Similarly, M0.2 saves the value of I0.2 from the previous scan cycle to compare it with I0.2 in the current scan cycle to determine if a negative has occurred. Let's study an application example of edge in the diagram below. To achieve an addition operation where pressing a button once increments the value in MW10 by 1, connect the button to I0.1. Without a P instruction after the I0.1 contact in the program, pressing the button will increment the value in MW10 by 1 in each scan cycle. If the button is pressed for 3 scan cycles, MW10 will increase by 3. Using the P instruction, as shown in the second network, ensures that pressing the button once increments the value in MW12 by 1, regardless of how long the button is pressed. This concludes today's lesson. We will continue in the next lesson.